Okay.
No, just
Kevin, we're ready to start.
Go ahead.
Thank you. So welcome to the session about statistical cryptanalysis of block ciphers. We are starting with a talk by Tug Thiessen, who is talking about a formal analysis of boomerang probabilities. And this is joint work with Andreas Bazen, Kinmos.
All right, thank you very much for the introduction. Luckily, we talked a lot about boomerang for the last 2 days, so I'm not going to give the full introduction again. 1 second. All right, so here we have a boomerang, a very classical one. So boomerangs were invented in 1999 by David Wagner to attack a block cipher named Coconut 98, but also in particular to disprove the idea that the absence of high probability differentials over the entire block cipher is sufficient to show security against differential cryptanalysis in general. So in such a boomerang attack, we have those 4 differentials, 2 on the top from alpha to beta and 2 on the bottom from gamma to delta. And we construct a boomerang distinguisher by encrypting this pair x0 and x1 with the difference of alpha, and then taking the corresponding ciphertext C0 and C1, adding difference of delta to both of them, and then creating this new ciphertext pair that we decrypt and checking for this, checking in the corresponding plaintext for this difference of alpha. And in this classical estimate, we assume that these differentials are independent, and that gives us this probability of p squared times q squared, which where p and q are the probabilities of those differentials. Now, we know already that this is a bit problematic to assume that it's independent. And in our work, we wanted to add some more evidence that this can be a bit of a strange assumption in the form of the following theorem. Namely, if we generally assume that we can treat those differentials as independent, then for every boomerang distinguisher, as the one we just saw, there exists a better normal differential over the entire cipher. So that stands in a bit of a contrast to the whole purpose of the invention of boomerang attacks. And I want to stress that I don't think this is true. I mean, you can easily construct pathological counterexamples. It's just something some of the strangeness you're into if you assume this independence in general. So the question that we posed ourselves was, can we construct a model in which we can formally state the probability of these boomerangs without relying on these independence assumptions? And as a starting point, we looked at how we usually treat differential cryptanalysis and how we calculate those the probability of differentials. So in differential cryptanalysis, we usually assume that we can treat the rounds as independent. And this is, of course, an idealization that one always needs to be a bit careful about. But in this model, we assume that we can treat the rounds as independent and thereby multiply the round probabilities to calculate very effectively the probability of a differential characteristic. So to create a mathematical model where we can that represents this property, we assume that before every round, a uniformly random vector is added onto the state for each pair. And the result of that is that we basically lose the information of the exact values in the pair and only look at the difference. So if we want to extend that for boomerangs, in boomerangs we don't deal with pairs of text, but we deal with quartets or 4 tuples of text. But apart from that, it's a relatively straightforward extension. So we assume that we add a uniformly random constant onto the state before every round for each 4 tuple of text. And that means we reduce the information contained in the 4 tuples to the relative differences between those 4 texts. When we look at, so what does that mean for those 4 tuples? So here we have a 4 tuple x0 to x3, and we can uniquely determine the differences between those texts by just stating the difference of the last 3 texts to the first text. So we can describe x0 to x3 by the 3 differences delta 1 to delta 3. And with this kind of representation, a boomerang attack looks like this. where we state all of the where we state the difference to the last three texts in each state with respect to the zero index text. And we need to introduce some free variables in some sense. So in the top, in the plain text state, it's this variable eta, and in the ciphertext state, it's this variable epsilon. But in principle, so this allows us to state in this model formally what the probability of a boomerang is. Check out the paper for details. And the nice thing that this model allows us is to prove some statements about boomerang probabilities. And I'll give two examples here. One is that for 2-round boomerangs on substitution permutation networks with 4 uniform S boxes, the probability of a boomerang deviates maximally from the classical estimate. So it's either PQ or it is 0. And this allows for both, this is both a problem if you're not careful with your boomerang, and it's both an opportunity for an attacker because you can construct boomerangs with much higher probability. And this has been used in a number of attacks already. And the second statement is kind of like in contrast to the first. We showed that the probability of a pair to follow the same trail corresponds to the classical estimate when you average over the separating distance of the pair. And the consequence of that is that you could argue, if you there are two things you can argue. One is that that the classical probability estimate of a boomerang far away from the middle layer corresponds quite closely to the classical estimate, so that the problems really occur mostly in the central layer. And the other one is that if you have a boomerang that is constructed of a large number of boomerang trails, so a large number of simple boomerangs, that the classical estimate is likely to hold again because you just average over a large number of these trails. And we'll give an example at the very end. Actually now. So we looked at 2 classical boomerang attacks on Serpent. One is the amplified boomerang attack by Kelsey, Kono, and Schneier, which uses 1 boomerang. And we just look at the interior 2 round of the boomerang, and that turns out to have a 0 probability. So that boomerang is just infeasible to find in practice. And the other one is the rectangle attack by Biham, Dunkelmann, and Keller, which is a more refined attack where a large number of trails in the top part and a large number of trails in the bottom part are considered, giving a total combination of roughly 2 to the 53.3 distinct boomerangs. And when analyzing the middle 2 rounds of those boomerangs, it turns out only 972 have a non-zero probability. And while the first fear one might have is that this invalidates the attack, it turns out that these boomerangs have such a drastically higher probability that the overall estimate is even slightly higher than the estimate given in the paper. So I think by a factor of 16. So to summarize, first we gave a proof that the classical independence assumption would make boomerangs superfluous. We formalized a model where you can state these boomerang probabilities in a mathematically pure sense, and we analyzed some classical boomerang attacks on Serpent in the considering this new model. Thank you very much.
Thank you. Are there any questions? Raise the microphone.
Thank you very much. I wonder what is the, when you talk about independence, I wonder what is the probability space, because you have many things. One, you have a key which is randomly selected. You have some messages which are chosen or known, selected at random. So when you talk about independence, so what is random?
So the randomness,
Yeah.
also, yeah. So the question is, so there are many sources of randomness in such an attack. You can from the choice of key, from the choice of plain text. The question is, where does the randomness come from that the probability is taking over in our model? So in our model, the randomness, all of the randomness goes into those random round constant that we add before the state. So we don't really look into keys. I know traditionally one says that you have these round constants are considered to come from the round keys, and we just use them just abstractly. But I think the argument you would make in practice is that this randomness comes from plain text, in a sense, from the linear part, in the plain text that is not going into the differences, and that you create some that this gives you. But the hope is that this gives you roughly a uniform distribution on those constants. That would be my argument. I hope that answers the question.
I will just check that there is a question online. It's okay. This one?
No, but just,
Chat.
I think you can go just swipe right again. No?
Link, do you know if there are some questions online?
I think they would be in the chat.
No,
Okay.
I haven't seen anyone.
Okay, thank you. So thanks, Tigo, again. So our second talk is about statistical model of correlation differences and relative key linear cryptanalysis. And Kaisa Nyberg is going to give the talk. Kaisa, can you share your screen, please?
Yes, I'm trying to do it.
Okay.
I'm sharing. I'm trying to share, but it doesn't work. It worked when I tried it. Can you? Oh, just a minute.
Seems to work.
Yeah, now here we are.
Can you put you in full screen, please?
I believe it is.
Okay.
Everything. I can start?
Yes, please start.
Yeah, okay. So this is my work. My paper was about related key linear cryptanalysis. In related key cryptanalysis, you compute correlations over linear approximation for two different related keys. And of course, you need statistical models to determine the complexity of the attacks. And now the problem is that there are all kinds of statistical dependencies over the data. For example, if you use the same sample to compute those correlations, and also over the related key pairs. For example, for the cipher, if there's some strange property for the related key which you want to use, you cannot assume that the related key pairs and the correlations computed for the related key pairs are independent. And my feeling was that this was not properly addressed in the existing literature, where we have kind of ad hoc statistical models making artificial additional assumptions, or just models stated without proofs. So my goal in this work was to fill this gap. For example, the first problem is that the correlations computed for even for a random pair of functions f and f prime are not fully independent, and we remove this artificial independent assumption. And the second problem is that over the data, the sampled correlations computed for two related keys k and k plus delta are not statistically independent. We give an exact expression of the variance of the sampled correlation difference without independence assumption, and in this way confirm and generalize previous statistical distributions of the correlation difference used that have been used for linear key recovery attacks. The main theorem is considers just a Boolean function, because the linear approximation is just a Boolean function. Define the correlation in the usual way, and the sampled correlation is the same but computed over only a sample of inputs. And then given a pair of Boolean functions f and f prime, and computing, we denote the difference of the correlations by c, and by c hat the difference of the sampled correlations, and then by q the probability that f equals f prime. So this is something that we need to state the result of the theorem, which is that the distribution of C hat is approximately normal with mean C and variance equal to this expression, where n is the size of the random sample and b is the so-called finite population correction coefficient if the sample is drawn without replacement, and we said put it equal to 1 if the sample is drawn with replacement. So assume moreover that over the related function pairs we have the C, the difference of the correlations, normally distributed from mu and sigma square. Then the distribution of C hat, we can give the integrated distribution over the data samples and over related function pairs is approximately normal with mean equal to mu here, and the variance equal to this the expression given here, where now Q is the mean over the probability Q, is the mean of Q, the probability of Q, probability Q over the related function pairs. So this is the main result. This formula doesn't appear, this expression doesn't appear in the paper. It's in the recorded presentation though. But we give in the paper we have these applications. If the for example, on the KD-IB cryptanalysis, key difference invariant bias cryptanalysis, given by Bogdanov and others in 2013, where the cipher, for the cipher, they consider two ciphers, L block and Twine, where these ciphers had the property that there was a key difference that kept the correlation invariant under when you compute the correlation of linear approximation, some key difference and some linear approximation where the correlations were equal. So it means that the mu equals 0 and also the variance equal to 0 because they were all equal to 0. But for random, we have mu equals 0 and as the variance is 2 to the 1 minus n. Then we can give the exact, or give the distribution of C hat. It's normal with mean equal to 0 and variance as given in this table. So with if sampling is with replacement, we have this variance in the random case, and for cipher we have 2 over n, while without replacement we have this 2 over n for random, and for cipher something less. So clearly, because the variance for cipher is less than for random, we are also here expecting to see that for cipher the variances are smaller. So the conclusion, we just consolidated the statistical premises of related key linear cryptanalysis, and we are looking forward to seeing new applications of related key linear cryptanalysis. Thank you.
Thank you. Are there any questions? So maybe I have one. So in the paper, I think you say you try looking at the multiple linear case. And do you have idea of to deal with this? And do you see any way to solve this?
Yeah, I mean, I think it can be solved, but it's going to be it's quite complicated. I mean, you have to consider over the multinomial distribution, and now there will be, because now you have two functions, not just a single variable, but you have two variables, and their joint multinomial distribution. So it's quite complicated. I haven't tried to do it, but this is for multiple linear cryptanalysis, assuming that the linear approximations are independent. We can just use this result I just showed to you. And for multi-dimensional linear cryptanalysis, it's not that easy because you cannot assume the linear approximations to be independent. But in the random case, my guess is that they behave as if they were random. Just quite a complicated thing to show, and I believe I don't think it's any fundamental problem. It just takes a little bit time and work to do it.
Okay, thank you. Are there any other question, maybe online? Okay, if not, let's thanks Kaisa again. Our next talk is also online. It's called Towards Key-Category Attack-Friendly Distinguisher Application to GIFT 128. And Weizong is giving the talk. Can you try sharing, please?
So wait a minute, sorry. Yeah, can you hear me and also see my screen?
Yes.
Yeah.
Can you be in full screen mode, please?
Okay. Okay,
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 yeah,
thank you.
please go ahead.
Hello everyone. My presentation is about the paper titled Towards Key-Category Attack-Friendly Distinguishers Application to GIFT 128. My name is Weizong and it's my joint work with Dong Xiaoyang, Peng Huifeng, Luo Yuan, Wang Si, and Li Zheng. Yeah, as a motivation, when we mount a differential or linear attack procedure, there are several steps we must do. The first is to find some wrong distinguisher, for example, with input alpha and output value beta with probability denoted by P. And the second step, we extend the wrong function at the top, and from alpha, and at the bottom from beta. Then we check the involved key base in the extended rounds. And at last, we collect enough messages and use statistical methods finding the right key value. So we've found that the first and middle step is to search out some valid distinguishers. And usually we do these steps as independent two steps. The first is searching distinguishers, and the second is attack procedure. And when we want to find a distinguisher, we really have two expectations. First, the distinguisher should be long. It means that the more long function can be extended at the top and at the bottom of a distinguisher. And second is low complexity. It means that when we mount an attack, less involved key bits should be in the extended round function. We found that both these two expectations are decided completely by the distinguisher's input and output value, alpha and beta. So in fact, some distinguishers are advantages when utilized to mount key-category attacks. It means that, for example, there are two distinguishers, but they have different input and output values. Then when utilized to mount attacks, these two distinguishers can have can lead to different attack results. So we propose a two-step strategy to search for distinguishers. The first one, we specify the input and output values in a set called the initial site. and we want the values in the initial set satisfying the above two expectations. More rounds can be extended from these input and output values. And second, the amount of involved key bits in the extended rounds is small. And second, we search for advantages distinguished with input and output values only chosen from the initial set given by the first step. So, and in our paper, when proceeding the first step, we use the MLP technique to search for the initial set. And actually, there are researchers can use different techniques to search for the initial set. And here is why we choose the MLP technique. First, the searching space of this step is very small. And the number of extended rounds is usually small when compared with the length of the distinguisher. And the second, the MLP technique is such an efficient. And as the MLP technique, it already values when we want to evaluate the security or some ciphers. So we didn't give the details how we can draw the MLP model. So we come to the result of the first step, the initial set. When we successfully construct the MLP model and get the initial set using the steps described in the first step, we collect all values that can be extended by most rounds, and also with some small amount of involved key bits into a set called the initial set. So once a differential with this input and output value differences is found, we can mount an efficient attack. The second step is the revisit of matrix branch and bound algorithm. And this algorithm guarantees to return all best trails for any initial value. So we think that it is very suitable for our second step. And also we have some dedicated settings. The first is only choose initial values from the initial set for sure. And the second is set the upper bound of active S boxes in each round the function to be 4. And the third is set the lower bound of the probability of valid differential characteristics to be to 2 minus 1 to 8. And this is our such algorithm. They have 3 sub procedures. The first one is initialization. It has the dedicated settings described above in the last slide. And the procedure 2, it's a recursive search. It's at the same as the matrix original search algorithm. And the last procedure 3, we record qualified results. And this is our strategy to search for different trails. And when we search for linear trails for gift 1 to 8, we use RAT instead of DDT to describe the linear mask propagation through the subcell operation. The inequality constrainability is the same as for the differential trail. And due to the fact that the interplay of the S both and the linear layer of gift 1 to 8 is well crafted to resist the linear cryptanalysis, we can not search out long linear trails when the upper bound of active S balls in each round it should be less or equal to 4. So we set T as 5. And this is our result. We apply our strategy to analyze gift 1 to 8 and search for both differential and linear trails. For linear trails, we find 20 round differential that can be used to attack 27 round gift 1 to 8. And this is the first 27 round attack on gift 1 to 8, which cover 1 more round than the other results. And for linear cryptanalysis, we find 17 round linear hole and give the first linear key recovery attempt on gift 1 to 8, which covers 22 rounds. And we also mount linear cryptanalysis on the most 2 notable gift-based proposals, gift COFB and Sunday gift. For gift COFB, we analyze the security of its 15 round version. For Sunday Gift, we analyze the security of its 16-round version. And here is my self-introduction. My research interests mainly includes symmetric cryptography, hash function, and AE algorithm. And now I work for high-tech startup in Shenzhen, China. Thanks.
Thank you.
Okay, thank you.
So I think we don't have much time for questions, so we will directly go for the next talk. And so the next talk is entitled Improved Rectangle Attack on Screening and Craft, and it's given by Hossein Najipur.
Thanks for introduction. Hello, everyone. Again, another work regarding boomerang cryptanalysis and another two concerning finding boomerang distinguishers. But maybe this one is a little simpler to understand or follow and maybe apply on other ciphers. This is the short presentation of our paper entitled Improved Rectangle Attacks on Skinny and Craft, which is a joint work with my honorable colleagues Nasser Bagheri and Ling Fan. Does work. The merit of our work is actually introducing a new heuristic method to search for sandwich distinguishers and introducing new tools in BCT frameworks using which we can formulate dependency in multiple rounds of boomerang switch. We applied our method on Craft and Skinny as two SVM block ciphers, and we managed to significantly improve the sandwich distinguishers of this cipher. Let me introduce very briefly the sandwich distinguisher. Sandwich distinguisher was proposed by Dinkelman, Keller, and Shamir, and it is actually proposed to take the dependency between the upper and lower differential transitions in boomerang cryptanalysis into account. As you can see in this shape, in sandwich distinguisher, we cut the block cipher E into 3 smaller slices, such that there exist good differential transitions for upper and for first and last slices. And these 2 slices can be connected to each other by putting a small boomerang distinguisher in between. For example, assume that there is a differential, there's a good differential transition, delta 1 to delta 2 for E0 with probability P, and there is another differential transition, for example, the nobler 3 to nobler 4 with probability Q for E1. To build the sandwich distinguisher in practice, we start with 2 plaintext P1 and P2 with difference delta 1, and we code the encryption of these 2 plaintexts to drive the ciphertext C1 and C2. Then we apply the difference noblet 4 and the derived ciphertext to generate 2 new ciphertexts C3 and C4, and then we query the decryption of these 2 ciphertexts to derive the corresponding plaintext on the other side, namely P3 and P4. And finally, check the difference between P3 and P4 to see whether the difference between them is delta 1 or not. The probability of getting difference delta 1 on the other side of this distinguisher is P squared Q squared R, where R is actually the probability of sending boomerang into the middle slice and getting it back on the other side. With this brief introduction, let's see what's the entire probability of sandwich distinguishers depends on. The entire probability of sandwich distinguisher is P squared Q squared R. P is the probability of differential transitions over the first part, namely E0. And it highly depends on the number of active splices over E0. Q is also depends on the number of active splices over E1. For R, we notice that it mostly depends on the number of common active splices between the upper and lower differential transitions over the middle slice. And according to the P squared Q squared R formula, we can see that the cost of active splices over the outer parts is higher than the cost of active spaces in the middle. So with this introduction, let me introduce our new method to search for sandwich distinguisher. Our method includes 3 main steps. In the first steps, we look for appropriate upper and lower differential transitions, in which we aim at minimizing the number of active spaces in outer parts as well as the common active spaces in the middle. Next, we instantiate the discovered truncated trails with concrete differential trails, and finally we compute P, Q, and R separately and put them together in P squared, Q squared, R formula to compute the entire probability of sandwich distinguisher. Let's take a look at the first part, which is the most important phase of our method. In the first part, given a block cipher E, we divide it into 3 parts, including E0, EM, and E1. Then we encode the propagation of truncated differential trails over the first R0 plus RM rounds with an MILP model, with a mode-based MILP model. We do the same for the less RM plus R rounds and make an independent MILP model. Then, to link these 2 independent MILP models to each other and encode the common active spaces in the middle, we define for every single spaces in the middle, we define an additional variable such as S here, and include 3 additional inequalities, as you can see in this slide, into our MILP model to connect the 2 MILP models to each other and at the same time encode the active spaces in the middle. Let's see how it works. According to these 3 inequalities, you can see that assuming that U represents the activeness of an S box in the upper trail and L represents the activeness in the lower trail, S is equal to 1 if and only if U and L are both equal to 1. It means that S is equal to 1 if and only if its corresponding S box in the middle is active in both upper and lower differential trails. Using this way, we can encode the common active boxes in the middle. We also include an objective function like this. As you can see, this objective function aims at minimizing the number of active boxes in outer parts as well as the common active boxes in the middle. We also assign some weights, some appropriate weights to the active boxes in outer parts as well as in the middle to find appropriate boomerang distinguishers. In the second step, we instantiate the discovered truncated trails with concrete differential trails. However, it should be noted that our distinguisher do not rely on the differential characteristic. As you can see in this shape, we only fix the differences at only 4 positions, which are the connecting point between the 3 slices of sandwich distinguishers, as you can see. Now let's take a look at the application of our method, our searching method for sandwich distinguishers on Craft. Craft is a lightweight recall by cipher, which was presented in FSC 2019. It's a very interesting cipher, and it has a lot of interesting properties. For example, all of its building blocks in its round function are involutory. I skip its description, and I just show the result of our searching method for boomerang distinguishers for Craft. This table summarizes our sandwich distinguishers for Craft. All of the probabilities marked in red have been experimentally verified. As you can see, in comparison to the, for example, simple differential analysis, boomerang distinguishers in the single tweaky setting have a great advantage over differential cryptanalysis in the single tweaky setting. For example, let's compare our turnaround distinguisher with a turnaround differential effect. The success probability of our turnaround sandwich distinguisher is 2 to the minus 19.83, whereas the differential effect for turnarounds is 2 to the minus 44. The advantage is clear. We also applied our tool on Skinny, which is another lightweight recall by cipher. This shape represents its round function. Depending on the number of involved tweakies and the block size, it has 6 main variants. We applied our method on all of its 6 main variants, and this is our results on Skinny. As you can see, in all cases, we managed to improve the sandwich distinguisher by 1 or 2 rounds. For example, let's take a look at this one. We managed to improve the success probability by a factor of 2 to the 37. We also built key recovery attacks upon our discovered sandwich distinguishers, and this table summarizes our results in key recovery attack. The top of this table represents our results, and the bottom represents the previous results. In all cases, we managed to improve the rectangle attacks by 1 or 2 rounds, except for one case, which is this one. However, we could improve its time and memory complexity in comparison to the previous work. Now we come to the end of this talk, and I would like to summarize our main contribution in this work. We introduced a new heuristic method to search for sandwich distinguishers. We also introduced new tools in BCT frameworks that I didn't discuss about them in a short talk, but you can take more details in our paper. We applied our method on two block ciphers, Skinny and Craft, which resulted in a significant improvement in rectangular text on this cipher. All of our codes to reproduce the result and experimentally verify them are publicly available in this GitHub repository. And thank you for your attention.
So we are a bit in a hurry, so I think we will keep the question for this afternoon, right? Yeah. Okay, thank you. Okay, so our next talk is entitled Accelerating the Search of Differential and Linear Characteristics with the SAT method, and Ling-Sung is giving the talk. And this is a joint work with Wai Wang and Mei-King Wang.
Thank you for the introduction. Can you see my screen?
Yes, it's all perfect. Thank you.
Okay, thank you. Let's start. In the last decades, the introduction of the automatic search boasts the cryptanalysis of symmetric key primitives to some degree. However, the performance of the automatic search is not always satisfactory for the search of long trails or cipher with large state sizes. Compared with the extensive attention on the enhancement for the search with MLP method, few works care for the acceleration of the automatic search with SAT or SMT. So this paper is motivated by this vacancy. The contribution can be divided into 4 parts. Firstly, we propose a novel method to encode Massur's bounding conditions. Following that, we provide a direction for the selection of the bounding condition. Then with the new methods, we obtain complete bounds about differential and linear characteristics of multiple ciphers. The first one is we give a related key differential attack on 26th round, gift 64. Partial clauses in a CNF formula regarding the search of differential or linear distinguishers should characterize the non-random feature of the trio. According to the specific goal, we should restrict the number of active S boxes, the differential probability, or the linear correlation in the distinguisher searching problem. All these kinds of constraints can be abstracted as a Boolean cardinality constraint, and this constraint can be converted into CNF formulas with the sequential encoding method. In this method, about n multiply k auxiliary variables should be introduced, and the number of clauses is also about n multiply k. We note that the sequential encoding method is based on the sequential counter circuit, and the circuit computes the partial sum for increasing the value of I from 0 to n-2. The partial sum Si is represented with k Boolean variables under the unary numeral system. With a careful study, we give 2 observations on the auxiliary variables in the circuit, and these observations are used in the encoding of the bounding condition. Firstly, the circuit already computes the partial sum of X with the index starting from 0. Secondly, the sequence of the partial sum is non-decreasing. After abstracting the bounding condition into the partial sum of the original objective function, we partition the discussion into 3 cases. In each case, with the circuit of the original objective function, we can establish the constraint on the partial sum. Note that the constraint can be converted into Boolean equation in CNF, and we realize the closal encoding for the bounding condition. The advantage of this encoding method is we do not claim new variables and the number of clauses is reduced. Now, since we generalize the bounding condition, we can create CR2-1 bounding conditions. So the problem is which sets of bounding conditions potentially result in extraordinary advances. To answer this question, we set up a series of tests on gift64 and summarize the strategy on how to select the sets of bounding conditions. According to considerable amounts of experiments for different primitives and our experience, these strategies can be generally applied to various block ciphers, even though they are expanded with the test on gift64. The new method is applied to several block ciphers. For present gift64, rectangle, L block, and twin, we obtain full information about differential active S-box, differential probability, linear active S-box, and linear correlation. As far as we know, we are the first one to provide all these results. Compared to the runtime with the MLP, the new method achieves significant improvements. For all versions in the Simon family of block ciphers, we obtain the full learning of differential probability and linear correlation. We claim that the result of the linear correlation is heuristic. The acceleration method is also practiced on all versions of stack family of block ciphers. Our research reached the maximum length of differential and linear trios among all methods targeting the optimal trio. We also use the acceleration method to evaluate the cipher with a 128-bit block size, gift 128. We get complete knowledge of active S-boxes from 1 round to 40 round. Moreover, we discover the optimal differential trios for up to 29 rounds and the optimal linear characteristics for up to 25 rounds. We also note that the acceleration method also can be utilized to speed up the search of related K differential characteristics. With this method, for gift64, we discover an 18-round related K differential trio with probability 2 to the minus 58. And with the 18-round distinguisher, we launch a related K differential attack on 26th round gift64. Lastly, we note that our result is far from threatening the security of gift64, since the authors recommended users to double the number of rounds under the related K attack setting. That's all for the presentation. Thank you for your attention.
Thank you very much. Again, I think we will directly jump to the next slide, next talk, sorry. So the next talk is Boomerang, embedding yo-yo with Boomerang and its application to Kyokuri attack on AES and Folkos. And Mustafiza Rahman is giving the talk. Can you please share your screen, please? Okay, thank you. We don't hear you. Can you try to talk?
Am I audible? No?
Yeah, it's all good. Thank you. You can start.
So this is a short talk on Boomerang, embedding you within Boomerang and its application to Kyokuri attacks on AES and Folkos. This is joint work with Dr. Dhimansa and Dr. Gautam Paul. So this work is based on basically two different cryptanalysis techniques, which are almost introduced 20 years apart. So first one is the Boomerang attack, which was introduced in 1989, and another one is the yo attack on spin ciphers, which was introduced in 2017. So here we saw the
sorry. I think we don't see the bottom of your slide. Can you put you in full screen, please? Full screen.
Yeah, this is full screen actually. Is my screen not visible?
Because we don't see the bottom of the slide.
Musab, this is Dhiman. Have you shared the entire screen or only the window? You should share the entire screen. Okay. Share the entire screen because the full screen will be a different window. Share the entire screen.
Is it not
Maybe try to no.
Now go to view.
Now put it in full screen. Put it in full screen now.
You must go to presentation mode.
Go to view. View on the top. On your PDF left, it's written view. On the left of your top of your PDF left.
Yeah.
Yes.
Yeah.
And choose view mode probably.
Probably I will just give it in this way. Is it visible?
Okay, that's better.
Let's try like this. Yeah.
Yeah. Okay. So in the left we saw the framework for the yo attack, and on the right we saw the framework for the boomerang attack. And yo is more related to the patterns instead of actual differences, whereas boomerang is more related to the actual differences. And this is quite a deterministic one, and this is more of a kind of probabilistic one. But yeah, some deterministic patterns are also available there. So our first result is that the Watson operation that occurs in the yo attack can be realized as a combination of the ladder switch and the S-box switch. So the ladder switch and S-box switch are actually a special construction in the boomerang attack where they captures the dependency between the upper tail and the lower tail of the boomerang tails. So by realizing the Watson operation as a combination of ladder switch and S-box switch, we now construct the framework for the boomerang attack. So in the upper part, this is the part of the yo part, and in the lower part, this is the part from the yo attack. From the boomerang attack. So here we give the probability of P, and here we need to pay the probability of Q square. And if the Watson operation occurs here, then we get this alpha dash with probability 1, where the zero difference pattern for alpha and alpha dash should be equal. So this actually increases the probability to PQ square. So we applied this technique to mount key recovery attacks on 5-round and 6-round AES. And additionally, we also saw an application on 10-round Falcos. So to mount the attack on 5-round AES, first we need to construct the upper trail and the lower trail. So we observed that if these are two AES states, and if these 6 bytes are equal for these two states, then the columns of operation here can be considered as the inverse diagonal swap. And this result is actually derived from special cases from the theorem 5 and theorem 6 from this paper, the exchange attack paper, which was in HACCP 2019. So when this actually these 6 bytes are inactive, then what we do, if we choose the lower trail as this part, so if we are exchanging here the inverse diagonal between the two cipher text, so this essentially means that we are actually exchanging here this column, and as these 3 bytes are equal for two different plain text, so this essentially means that we are actually swapping the inverse diagonal. So as our upper part is SLS layer here, so the yo attack occurs in this upper part deterministically. And then we get a pair of plain text whose zero difference pattern should be equal to that of alpha. Next, we extend this attack to mount a key recovery, to convert this to a key recovery attack for the 6-round AES. For this part, we prepend here 1 round in the beginning. So here we choose the difference in this form, and we expect that here 1 byte will be active with this probability. And from here, we employ the Boolean technique. And here with some probability, with this probability, this byte will be inactive, and thus in the end we'll receive this pairs, this kind of pairs with this cumulative probability. Now, the problem here is that in addition to the right pairs, here we also can obtain the wrong pairs, and the right pairs and wrong pairs both will suggest a pool of right and wrong pairs. The problem here comes to how to distinguish the right pairs from the right key candidates from the wrong pairs. So for this purpose, what we did, we used the notion of signals to noise ratio, and we found out that for AES, if we consider 10 right pairs, then we can successfully filter out the right key candidate from the wrong key candidate for a column case. So now we use the same technique to mount key recovery attack on 10-round Falcos, and this technique is quite similar to the attack that was mounted on 6-round AES. And in this case, we found out that 2 right pairs are enough for detecting the right key candidate. These are the attacks and with the complexities that has been reported in this work. And so finally, we have devised a new generic strategy which has combined the Yo with the boomerang attack, and we have shown that the Watts operation can be considered as a combination of the S-box switch and the ladder switch, and we have applied this technique to mount key recovery attacks on 5-round and 6-round AES and 10-round Falcos. And the attacks on the AES has been verified by employing them on the 64-bit version of the AES. And we hope that this provides a better understanding for AES and AES like ciphers. Thank you.
Thank you. Maybe we have time for a quick question before lunch break. So maybe I have one. Do you think it would be possible to do automatically the search of such a distinguisher?
I didn't get you.
Do you think it is possible? Yeah. Do you think it is possible to automatically search for such distinguisher?
Yeah, I think it may be possible, but actually we have to think about that, but still we are not able to do it, but we think that may be quite possible.
Okay, thank you. Let's thank all the speakers of this session again, please.
Thank you.